Great.
Thanks, Costas. And it's great to have such a good attendance. So basically, when on the 2021 IATBR conference, we thought that it will be good to arrange some online events to keep us connected. We also felt that it will enable us to reach a wider global community of travel behavior researchers who may have missed out actively participating in our IATBR events due to various constraints. So before introducing Thomas, and I also wanted to mention again that Giovanni and UC Davis conference support team provided enormous support to make this a reality in terms of technical terms, and many thanks to them again. So in our first event, so we planned 3 events. So this is the first one, and then we are going to have another one in August, and the third one in November. So all featuring like the past IATBR Eric Pass Dissertation Award winners or honorable mention recipients. And we thought it will be also good to have the past IATBR Lifetime Achievement Award winners as discussants, so that like they can also provide insights about how this research fit into the kind of wider aspect of travel behavior research and what is the future of travel behavior research. So today we have the 2019 IATBR Eric Pass Dissertation Award recipients, Dr. Thomas Hancock as the main presenters, and Professor Tommy Garling, the 2018 IATBR Lifetime Achievement winner, has kindly agreed to be the discussant. So I will just say a few lines about their bios. So Thomas obtained his PhD in choice modeling and travel behavior research from the University of Leeds in 2019. And I was fortunate to be one of his co-supervisors along with Professor Stefan Hess. So since finishing his PhD, Thomas has continued working at University of Leeds as a research fellow. His main areas of interest are understanding the decision-making process, the integration of econometric choice models and mathematical psychology, and also to better specify the models, better interpret various types of kind of challenging behaviors like moral choices, for example. And work thus far has focused on the implementation of decision field theory and ideas from quantum cognition in choice modeling. So today he will be presenting his doctoral research on travel behavior modeling at the interface between econometrics and mathematical psychology. And as mentioned, we have Professor Tommy Garling as a discussant. He got his PhD in psychology from Stockholm University in 1972. He was assistant and associate professor of applied psychology at Umeå University, and later research professor of psychology and planning at the same university. In 1992, he was appointed as professor of psychology at the University of Gothenburg. He has also held positions at the University of California, Berkeley, Irvine, and Santa Barbara, University of Virgin, Aarhus Business School, Karlstad University, and Royal Institute of Technology in Stockholm. His research focus over the years has ranged from fundamental research in spatial cognition and judgment and decision-making with applications in navigation and orientation in the environment, route planning and travel choice, and residential choice. In recognition of outstanding and sustained contributions to the field of travel behavior research, IATBR awarded him the Lifetime Achievement Award in 2018. So without wasting further time, I would like to give the floor to Dr. Thomas Hancock. And just to mention, if you have any questions, just type them in the Q&A box. We will get to them at the end. Thanks.
Hello, everyone. Can you see my slides just firstly to check?
Yes.
Yes, great. Okay. So firstly, thank you for inviting me to give this talk today to the IATBR board who set this up. And congratulations to Pat with the awards. Really inspiring hearing about all of the things you've done and the recommendations you got, and the praise was just incredible. So today I'm going to give an outline of my PhD. It's going to be, I'm going to try and keep it just a sort of outline, because to go into too much detail would take too much time. So I'm going to give a little flavor of everything that was in it. And hopefully, if there's one particular topic you're interested in, you can go away and have a look, and I'll be more than happy to speak to you about it in more detail if you ever have questions.
Thomas, can you see if you can make it a slideshow or something, because we can also see the sidebars.
Better?
Yes, that's better. Thanks.
Yeah, perfect. Okay, so yes, I'm going to be talking about travel behavior modeling at the interface between econometrics and mathematical psychology. And the first thing I should say is I'm not trained as an econometric person or as a psychologist or a mathematician. So I'm actually kind of well placed to be in the middle between these two. And I think that's really helped me with my topic. So I'm going to start with a few examples of stated preference choice tasks here. So here's one from Transportation Research Part A. And this is looking at whether you're going to move location and how much salary you need as an increase for a longer travel time. Second one, this is from Kaspar's taboo trade-off data set. This is in the general choice modeling. Here's a new transport policy. Will you accept it or not? The third one, this is on apartment choice. So which apartment are you going to choose? And there's various attributes of this apartment. And this one's in cognitive psychology. So three very different journals, but all really rather similar in the case that we're answering stated preference choice tasks. So my question here is econometrics and mathematical psychology maybe not so different. So both regularly consider stated preference choice tasks, both attempt to understand preferences of individuals, both account for heterogeneity in preferences, but in rather different ways. And then there's contextual effects, question order, impact of other alternatives. All of these are considered by both fields. Both of them have a number of different models and different ways of explaining behavior. So really, they look quite similar at the face. They're parallel streams of research, though, and there are not actually many bridges at all between the two. So what my thesis really was trying to do is bridge the gap. So here is another stated preference choice task, and this is actually my morning commute. These are the alternatives I had pre-COVID. I've been working from home for the last almost a year, 3 months now. So this was my morning commute. I had 4 different options, and I wonder if normally I would get people to do a show of hands and see alternatives, but obviously I can't really do that. I can't see you all. And so just have a look yourself and think for a moment, which alternative are you going to choose? Is it going to be the national train, which is faster, a local train service, a bit slower? You're going to get the bus, or you're going to drive yourself? Just take a few moments to think about that. I'll give you a few seconds. And now I'm going to then talk about different ways we might have made this choice. So how might we have made this choice? Well, for a start, we could have done something systematically. So imagine I'm going to make this choice here. So I'm thinking maybe I particularly like going on the train. I can continue to do work on the train. I can phone family or something. You know, I can use my time when I'm on the train. It's a quick train. It's only 20 minutes, but the rate of crowding is pretty bad and the cost is high. So there's 2 positives, 2 negatives. I'm going to give that a score of 0. I can do this for the rest of the alternatives. So local train, yeah, I said I've liked trains. 50 minutes is long though. Cost is good though, so it's cheaper than the national train. Then I look at bus and think, no, time's bad, rate of crowding is good though. So that's also going to get a score of 0. Car, however, it doesn't look too great when I consider the number of delays. The roads in and around Leeds University are quite busy, so I'm not too keen there. So in this case, I've ended up choosing the local train. It's got the most sort of positives relative to negatives, and I choose the local train to get to Leeds. Now, instead, I might do it more systematically, but by attributes. So if I look at all the different travel modes and I think, actually, car is my least preferable there. It's the one I'm least likely to be able to do I'm not going to be able to do anything else. I'm going to be focusing on driving. Time, well, the bus and the local train are the longest, so they get negative marks there. Rate of delays, car is going to be the worst. Rate of crowding is obviously if I'm on a train, bus and car aren't going to be so bad. And then the cost, the worst, is the national train. So now it's a different choice I make. I'm making the choice of bus. It's the one with the least negatives. So I've done two different ways here of thinking about how I might have made this choice, but there's some inconsistencies here. So firstly, I've assumed that decision makers consider all of the available information. I've looked at everything there and I've gone through it step by step. The utility of the alternative is not directly affected by attributes of others, or at least not in the first case, it was in the second. The utility obtained from alternative is constant. So I'm saying here that it is just a sort of fixed number. And the information is considered in some sort of systematic way. So you'd have seen when I presented that there how I did these systematically. So in mathematical psychology, what if we instead assume that the decision-making process is less systematic? And this is something that is inherently really important in their models. So here, what we've got is dynamic preference over time, and we're doing some sort of attribute comparison. So imagine we've got some sort of preference value for these different modes when you first look at this, and then you're going to start comparing the alternatives, comparing them across different attributes, and updating your preferences. And this is supposed to be a sort of almost mimic what is actually happening in your brain. It's a sort of outline of a deliberation process. So in the first step, I've considered the time. National train looks good. My preference value for national train increases. For the other three, it decreases. I might continue to deliberate, consider the rate of delays, for example. The trains look good. And then this pink option, local train, has reached the preference line here. So this is saying that one of the alternatives needs to reach a value of 3 for me to choose it. So maybe in this case, I've ended up choosing the local train. However, what might happen is that maybe I'm particularly fussy and actually it takes more for me to be convinced. I continue deliberating instead, consider the other attributes, I look at the different factors, and I end up choosing national train. Because at some point I'm going to have to make a decision. I'm going to have to go out and get to where I need to be. I can't just sit at home forever, even if COVID means that that probably is what will happen. So in this case, I've chosen a national train, and basically what's happened is that the initial bias has had less of an impact the further longer I've taken to make the decision. So this is quite, I guess, complex way of simulating the decision-making process. Alternatively, you could try and do something a little bit more simple. And this is one of the different models within mathematical psychology. Is based on a linear accumulation of preference. So what happens here instead is that you still have this idea of initial preferences, but then once you've considered all of the information, you have some rate of increasing preference for each alternative. So what happens in this case is that depending on how long you consider the alternatives, you may still choose different ones. So in this case, local train was my initial favorite, but if I continue to deliberate for a longer time, the bus ends up overtaking. I end up choosing the bus. Another different way you could consider choices is something that's really rather inherently more random. So this is saying that there's actually a lot more randomness in the decision-making process. So we've still got some preference level for each alternative, changes over time. There is fluctuations during the decision-making process due to considering different attributes, but also just due to noise. What we see here is preferences of waves. So imagine that this is the sort of preference values for each alternative, and you exist somewhere in a sphere. You're sort of spinning around. There's still some randomness at the end of the deliberation process in this version of this model. So the decision maker still makes a choice, and there's still some randomness there that, in another day, you might still see all the same information and make a different choice. So these models that I've just talked about, the first one is decision field theory. So this is the dynamic stochastic preference evolution. It was first introduced in 1992, and I actually went back and looked at the precise date of the paper, the journal it was in. This model is exactly a month older than I am. It was expanded to multiple alternatives and multiple attributes, and then in our paper, we moved it into the travel behavior domain. So that was my first PhD paper like a few years ago now. It attempts to capture this stochastic nature of deliberation. One of the key aims of the model is to capture contextual effects. So this is one of the reasons it was originally developed in the first place, was to capture effects found by behavioral economics, for example, cognitive psychologists. Then there was the linear ballistic accumulator. This was introduced in 2008. This is a different model, where it's been described as the simplest model of preference accumulation. So it's still capturing that sort of mimicry of the deliberation process, but it's actually been designed to be mathematically simple. Now, if you read the paper that I've got on these two models, I actually say DFT is simpler mathematically. It depends on what sort of background you have, but for me, implementing decision field theory was actually easier. It performs well on perceptual tasks. I think this is why cognitive psychologists really like it. It's really very good at things like the adopt motion direction task. So this is sort of a task where you have to, it's not just testing preference, it's testing other things about how the brain works. And then there is quantum probability choice models. So this is when I was talking about preference behaves like a wave. That's the sort of inherent idea here. So this is ideas borrowed from physics. So where instead of saying particles or light are sort of behaving in a certain way, we're now talking about preference and comparing preference to those fundamental concepts within physics. And this basically means that we're instead assuming that a decision maker is inherently uncertain. So within a standard models, we're usually saying that it's the analyst who has some uncertainty about the preference values of the people. So we can see some of the things that might influence people's choices, but there's still some inherent uncertainty from our point of view. In this case, we're saying actually no, the uncertainty is still with the decision maker. But the decision maker does have some belief state. So this is how they sort of have information, how they store information. And they only consider preferences for alternatives when they're explicitly asked to. So this is really kind of one of the key core psychological principles here, which I think is actually really insightful. So basically what that is saying is that if I'm not thinking about whether I prefer a train or car, then I don't have a preference, train or car. It's only when someone asks me, do you have a preference, train or car, that I think, oh, which one would I choose? And that's one of the key concepts that's built within this model. And what we find with this model is that it's got really good, efficient transformations for change in choice context. So for example, if you have a behavioral nudge, this model is really very good at coping with that sort of thing. So here we've got an example where I'm considering two different travel modes, car or train. And what this is saying is that if I ask myself, how environmentally friendly am I? I'm then going to be more likely to choose train. So basically, I've got this initial preference state, and I converge towards choosing train if I say that I am environmentally friendly. So why haven't these models been used within sort of larger sort of scale travel behavior choice modeling? Well, firstly, they're computationally intensive. Decision field theory takes about 100 times more longer to run than standard multinomial logic, in my experience. You cannot equivalently obtain willingness to pay measures. The decision-making processes may be perhaps not considered to be so vital. We're really kind of focused on outputs. And certainly from the psychologist's point of view, they'd say of travel behavior modelers, they're really looking to understand outcomes. They're not as concerned about what actually happens in the brain. And they do not often include clear methods for incorporating heterogeneity. So quite often, because of the way they do experiments within cognitive psychology, they do large numbers of trials, and I don't mean sort of 10 states of preference choice tasks, they do 200 perceptual decision-making tasks. So, you know, they end up with enough data to do a model per person. So it ends up looking quite different because they've got these sort of models per person rather than one model trying to incorporate heterogeneity across different decision makers. And there's mathematical language barriers, without a doubt. We speak different languages. And that's clear just within our own field. We've got so many different names for the mixed logic model. There's one good example. So that is a hindrance as well. Also, these models are often not generalized for different contexts. So quite often they're built to explain one specific paradigm, so one specific experiment, and then they do something different, then a new model for a different case. So the aims of my thesis were ultimately to bridge the gap between mathematical psychology and travel behavior and choice modeling. So there's a number of steps we really considered here to do this. So it's to create tractable methods for applications of preference accumulation models, develop a choice model based on quantum logic, to compare models, and then to identify when these models are really kind of useful to be, when we should make the move to these models. And then finally, looking at ways of combining approaches in different disciplines. So this is a sort of outline of my thesis, and if there's a particular paper you're interested in, please do, ask me questions later if you want to go and have a look at it. I'm more than happy to speak in more detail. But this is just an outline. This is a sort of summary of what the different parts of my thesis were. So firstly, looking at improving the mechanisms for decision field theory. How can we actually apply this to our data? Secondly, can we incorporate choice response time into decision field theory? Third was do a more rigorous comparison of DFT, the multi-attribute linear ballistic accumulator model, and econometric choice models. Fourth was to develop a quantum choice model, then to apply it to moral choice data. Steps towards these models, making these models more realistic for dynamic data. So for example, driving behavior data. And then a couple of papers on model averaging, where we're looking at bringing these ideas together. So I'm just going to do literally 2 slides for each of these, just to give an outline of what the work I had in my thesis. So chapter 1 outline. So it's mathematical improvements to the underlying mechanics for decision field theory. So one of the main issues with decision field theory before is that there wasn't really sort of good methods for calculating probabilities of alternatives kind of over time. So what I've got here in this graph is 4 different alternatives. This is no longer preference, this is probability over time. So this is probability over time. So the longer you take in this case to make your decision, the more likely you are to choose the yellow alternative. And equivalently, you've got a high initial bias for this green alternative, and it's gradually decreasing over time. And what the work in this paper does is it allows you to calculate these probabilities no matter how many number of preference updating time steps you have here at the bottom. And this makes the model far easier to run analytically, and we're pleased to say that this is now on Stefan Hess and David Palmer's Apollo. So in the Apollo choice modeling package, you can now run decision field theory models. Easier calculation of probability of alternatives, and you have these steps, which is really great. And then, of course, we did our first application to travel behavior, state of preference tasks. Here's some of our results. We had a Swiss and a UK value of time type state of preference data. And we found that our DFT model outperforms the multinomial logic model. Now, I mentioned before that you don't have equivalent sort of value of time measures from DFT models, but you do have what we call relative importance of time. So it's saying something about the relative importance of these different parameters, and that shows that we have slightly lower, in this case, results than the value of time from MNL. And I will need to test this in more detail to see how consistent this sort of finding is. We also found that there was multiple mechanisms for incorporating heterogeneity, both across and within decision makers within a DFT model. This is something I previously said these models weren't great at, but we found actually we can do this pretty well. And we demonstrated that we could do a sort of mixed DFT with random parameters, and that worked pretty well as well. Chapter 2, so now because we can put this number of time steps at the bottom here where we're saying we can estimate this value, we can then try and link this to response time as well. So what we're saying here is that so what I'm saying here is that in this case, what happens is the longer that you deliberate, the more likely you are to choose this alternative. So if I have some information about the response time, then what that theoretically could mean is that if I make the decision very quickly, the model is going to predict more certainty that I'll pick the grey alternative, so slightly more likely, but the longer I deliberate, the more likely I am to choose this alternative here instead. So there's two key reasons you might be slowed when responding in stage preference, for example. One is that you're being careful, and you're deliberating carefully over the alternatives and making a careful choice. The other is that you could be uncertain, you just don't know, you're taking a while because you don't really know how to differentiate the alternatives. So two very different reasons, and what we're saying in this paper is we're aiming to disentangle these confounded sources of increased choice deliberation time. And the model itself inherently says that probability for one alternative will increase over time and decrease for the other one. So what we found was that response time can be incorporated into DFT models to improve the accuracy of them. And that some decision makers seem to be careful thinkers, but for more decision makers, faster decisions are more deterministic from the perspective of the model. So I'm not saying that this is necessarily that they're necessarily making quick decisions, but they're basically what I'm saying is that those decisions are more predictable from the model perspective. But what we found was that the parameter for the number of preference updating steps actually appears to have a very similar role to the scale parameter in a random utility model. So what we've got here is the response time along the x-axis, and here is the scale parameter within an MNL model, and this is the response, the time step parameter within DFT, and we ended up seeing something very similar. So this initial suggestion says that this isn't really a time parameter; it's actually a scale parameter. So the psychologists have perhaps got this wrong, what they think this parameter means. So this is some work that needs. We're still finishing working on this before we submit this to a journal. But what we're saying is that it looks like the parameters may not mean exactly what they are psychologically meant to mean. Right, so chapter 3, this is where we did the more detailed comparison between models, decision field theory and the multi-attribute linear ballistic accumulator. And one of the key things we've done in this paper is to provide sort of detailed analysis and guidance for how to apply these models. So this paper, we were pleased to say, was accepted for publication in Transportation Research Part B just last week. So this is fresh, and you can go and have a look at this in detail now. And this will guide you, give a sort of rough guidance on how to use DFT within Apollo as well. So this should help if you want to go and actually try these models for yourself. And what we do in this paper is rigorously compare DFT, MLBA, MNL, and random regret as well across both SP and RP datasets. We find that both of the psychological choice models do pretty well. DFT does better for the SPs, MLBA for the RP. And we again find relative importance of different parameters, but we actually find there's very few significant differences across the models, both across the psychological and the econometric choice models. And we find that theoretical and empirical identification is important for both DFT and MLBA. And what this means is that the sort of psychological process parameters within the model sometimes help but are also sometimes ineffective. So you have to be really careful when you're specifying these models, and there is information in this paper on how best to do that. In chapter 4, we look at quantum models. So basically, what's been done so far is that cognitive psychologists have basically come up with this new field, quantum cognition, where they do a lot of models based on a quantum framework. Now, it isn't quite sort of choice data, so it wasn't just ready just to go and apply a sort of travel behavior data set to this. We had to think about how this would actually work. But the quantum, I think I've outlined a few reasons for why you might want to use a quantum model. They're very, very good at contextual effects and ordering effects, which we have in travel behavior, crucially. And we wanted to see whether we could use quantum theory to make a choice model. Now, we do two very different outlines. One is we call the amplitude model, and the other is the Hamiltonian model. And what we find is that across many different case studies, actually the value function has a really strong impact. So you have to be really careful about your model specification in the first place. But once you've got that right, we found quite a few successes for the amplitude model in particular. DFT sometimes did slightly better, but the quantum amplitude model did very well as well. The next bit was Casper Koros was very kind to share his taboo trade-off data set with us, and we applied our quantum model to that. And how this came about was that he had a call for new work and new models on moral data at the last International Choice Modeling Conference. And we thought, well, we've got this new model here, how about we try and apply this to moral data? And that has actually often been done in a sort of context, cognitive psychology context, just not in a sort of large travel behavior context. And what we found was that the quantum model can again really do a good job of capturing sort of changes in perspective. So is there a taboo or not? The quantum model does a nice job of doing that. And what we find is that the model does a really close match with the observed shared accept policy, whether people accept or not. So the orange bars here are the deviation from the true value for how many people accept policy or not. And we see really quite small deviations from the quantum model in comparison to MNL. However, what we also found was that there was no particular evidence to say that the quantum models were particularly suited to moral choice data. They seem to do quite well in general. Chapter 6 is about dynamic data. So here's a case study where we've got some preference evolving over time. But suddenly, one of the alternatives changes. So alternative 2 was £10 and suddenly drops to £6, and suddenly it looks a lot better. So we wanted to consider whether we've got an inherently dynamic model that is also better for inherently dynamic data. So what we have is driving behavior data, and we're going to apply both the decision field theory and the quantum Hamiltonian model to this data. Both of these are sort of more inherently dynamic models. Again, we found there was some differences, not very much if you don't include memory. So in terms of if you don't have sort of a static case, but if you start moving towards a truly dynamic case, then the model starts to do a bit better. And the quantum one in particular was the best model in this case. And we could find reasonable model outputs for this driving behavior data, such as the gap behind a merging vehicle is more important than the gap in front. So you're more wary, basically, of what's behind you than what's in front of you when you're merging lines. Finally, model averaging. So this comes about from asking the question, how do you choose your final model? Well, actually, you don't have to. You can do model averaging instead. So here, what I've got here is random utility model and decision field theory. They've both got their benefits. They both work in very different ways. But what I can actually do is combine them in the model averaging approach. So model averaging, the way we use it is a sort of restricted latent class model. So what this means is that rather than having a latent class model where we estimate everything, we're going to have a random utility model which we estimate, decision field theory which we estimate. We get those betas, we plug them into our latent class model, which has the components random utility model in one class and decision field theory in another, and then we're only going to estimate the shares in this final model. And what the real benefits of this are is that you could have hundreds of models in this top level. So we've only got 2 here, but you could have many, many and combine them. So obviously, if you had a latent class model with 100 different classes, you're going to have estimation issues. But that's not the case. If you've got 100 separate models here, and then you combine them. And the nice thing is, if you have one model that really does do a lot better, then it's just going to get 100% of the share. So if you do have one model which is really representative of behavior and is the best model, then it's going to get 100% of the share and you're good. Now, the other nice thing you can do here is that you don't necessarily need to know anything about the different model components. So for example, I could ask 10 of you to go and run a model on a particular data and come up with your own model. I then get the probabilities for each data point from each of your models, and I then could do this model here. So it's quite a nice way of avoiding risk. And as a result, model averaging is used a lot in, for example, weather forecasting, but we don't really do it yet in travel behavior. So key findings, we did find that there was a number of case studies where we found consistent improvement in both in-sample and out-of-sample model fit. So for example, we combined different mixed logic models. We did different treatments for non-linearities, models with logical arithmetic or linear cost, for example. And then a number of models for different nesting structures. So for example, here's a map of California, and how do we do mode and destination choice in this data set? So do we have nesting within the sort of county level? Is it more regional, maybe north, south, east, west? And we looked at these different possibilities and found that you could do model averaging across this. Final paper was looking at specific outputs for model averaging regarding what types of heterogeneity we capture in the different models. So what we're really saying here is that model averaging, the way we imply it, does not capture taste heterogeneity. So if I've got this model explaining every single person and this model explaining every single person, and then I fix the betas, then there is no way to account for taste heterogeneity in the two different classes. But if I estimated all of them separately, I could account for it. So basically what I'm saying is that if I compare my model averaging compared to latent class, the latent class model will pick up a lot more taste heterogeneity than the model averaging one will. And this will tell us something about what are the true underlying sources of heterogeneity in our data. So we had two case studies. The first one, we found absolutely zero gain from using model averaging, which suggests that all of the gain was from taste heterogeneity rather than, for example, decision rule heterogeneity or attribute norm attendance. The second one, we had quite a bit of model averaging, suggesting that there was, still mostly taste heterogeneity, but there was also some decision rule heterogeneity, clearly from our data. So there are numerous next steps for these models. I think this is, I would hope, that only the beginning of the sort of bridging the gap between mathematical psychology and econometrics. So for example, can we also bring it in machine learning? Can we also really examine the decision-making process and link associated process parameters? So that's when I'm talking about the number of deliberation steps, linking that with response time. Or for example, eye gaze movement, where I'm looking, can I link that with the importance weights for different parameters, for different attributes, incorporation of physiological data, for example. Further comparisons of outputs, so we need to better understand all the measures that can be obtained from these models. So basically, for example, my relative importance of time, how does that really compare to the value of time? And then further steps towards truly dynamic models, better models for modeling driving behavior, for example. And these are only a few examples. Now, I thought I'd finish with a slide, a couple of slides. One, a few comments for future applicants of the Eric Pass Awards, or for new PhD students in general. So first, my first bit of advice is to be brave. Try and think outside the box and step away from the tried and tested. If your work's not novel, it's not going to stand out quite as much. Now, I'm not saying you have to come up with new things for everything. It's not. You don't want to be new for the sake of it. That's a really bad idea. What I'm saying is that try something different and just try it out. If it doesn't work, it doesn't matter. You can do something else. That's all right. But try and be brave. Elaborate new theories mean nothing without solid empirical applications. So what I mean by this is that if you come up with some really nice new theory but can't apply it to data, what have you gained? You're not really gaining anything. So I think this is probably, would be my guess, would be one of the reasons I won this award, was that all of my papers, all of the chapters had theory, then empirical application. So I always backed up what I did theoretically with empirical work. And I think that's really, really important. And this is something that cognitive psychologists are really bad at. Not so much travel behavior people, we're better at this, but cognitive psychologists are, and this is why there wasn't really a quantum choice model, because they come up with all these elaborate theories, nice theories, they hadn't applied it to data. Don't try to be too clever when you're writing up your work. Your reviewers will get lost and lose interest. So what I'm saying there is that don't skip mathematical steps. I'm really guilty at this actually myself. And I know I've had several comments from both my supervisors and reviewers saying, "Oh, what have you done there? You know, what's that step there?" You're going to waste time. So try and really label what you're doing. Try and teach people what you're doing. And if someone doesn't understand, then you've lost your arguments. You know, you really have to back up your work with proper explanations. Next thing, take a step back. Remember to look at the bigger picture. So my best example of this was after, I think, about a year of my PhD. I had a meeting with my supervisors, with Stefan and Charisma. And I remember Stefan saying to me, "Are you going to be Mr. DFT?" And I hadn't thought about it until that point. But when he asked that question, that was me taking a step back and saying, "Are you going to really focus on decision field theory?" And I thought at that point, I can't be boxed into looking at just one model. And that's when I thought, no, I need to go and look at these other models and see what else I can do. It's really important to think about the bigger picture there and think about where you're going with your work. And finally, pay close attention to reviewer comments and present your work as often as possible. So over the course of my PhD, I must have given maybe 15, 16 presentations. TRB deadline is really great. Really use that. So that's a really nice point to try and force yourself to get your work down on paper. Stop running new models, stop trying to come up with new things and actually get work out there. And that would be my final suggestion. And one final thing is try and enjoy yourself. That's really important. Finally, if you found this presentation interesting and you want to know more about the work by people at CMC, I'm pleased to announce that the Choice Modelling Centre has a new online seminar series featuring 3 of my fellow recent PhD graduates. And there's the link for the seminars, starting with Evangelos, who's going to present his work on driving behaviour next Tuesday. It'd be really great to see as many of you there as possible. And that's it. Thank you very much.
Thanks, Thomas. So we are slightly running behind the schedule, but I think we can make it up. So I would now like to invite Professor Tommy Garling to discuss about Thomas's work and also about the future research potential in this direction.
Thank you very much. Do you hear me?
Yeah.
Yes.
You do? Fine. Okay, let's see if this works now. I'm not very... Can you see it?
Yeah.
Yes.
Okay, fine. Yeah, first of all, I want to congratulate Thomas to an admirable intellectual achievement. Given my background in the psychology of judgment and decision making, JDM, I'm also enthusiastic about that he has applied some work in that field. I furthermore thank the organizers for asking me to comment. Since the decision field theory, DFT, proposed by Bussemeyer and collaborators is an important point of departure for the dissertation, DFT will be the point of departure for my reflections as well. In my opinion, DFT is an interesting formal model of the deliberation process preceding a decision, which has been studied in JDM for many years. It's a different, but not the first and only application of psychology to travel behavior research. Early travel behavior researchers became interested in Fishbein and Eisen's attitude theory, and this interest appears to be sustained. Also, some have used Kahneman and Tversky's prospect theory, featuring reference-dependent utility, loss aversion, and nonlinear probabilities, differing from conventional expected utility theory. In the dissertation, stated and revealed preferences, one-shot choices are modeled with DFT and extensions of that from quantum cognition. And I think it's clear that better fit to data than McFadden's random utility model. Now I will reflect on what advantages and disadvantages DFT has compared to these other applications of psychological theories. So in contrast to my examples, the DFT is a process model. It is quantitative, and like my examples, except some variants of attitude theory, it ignores the possible role of emotions, despite its current strong influence on travel behavior research. Now, instead of giving a kind of detailed feedback on Thomas' dissertation, which I obviously cannot do better than his advisors and the reviewers of his submitted papers, I will raise some general questions. My examples of previous influence of psychology are structural models and not quantitative process models. So why process models and why quantitative models? Last, I will raise an overarching question. What is the relation between choice and satisfaction with the outcome? This is important in as much as the focus of travel analysis is travelers' emotional well-being, which is the kind of emotion that matters when people travel. So, why process models? Well, process either refers to mental transformations of information with the goal of making a decision or intention, forming an intention, resulting in a choice, that is behavior, or the external process of interaction with a changing environment, partly depending on previous choices, with the goal of making adaptive sequences of decisions and choices, for instance, in driving a vehicle. In real life, these types of processes are integrated. Distinction is also made between low-level and high-level cognitive processes. Early research on decision-making in psychology assumed that conscious thinking dominates the decision process, which was possible to reveal by means of verbal reports. Think aloud, information search, eye fixation, and physiological methods were used, often in combination for cross-validation purposes. In computer simulation models, the data were considered as a sequence of states with the goal of understanding the mental transformations of states, similar to debugging computer programs. DFT proposes a sequential sampling model of information acquisition, which after estimating several free parameters predicts observed choices. Process and tracing methods are not feasible in the short time scale, characterizing low-level cognitive processes in general. Measures of decision time is then another method to infer type of processing. I'm not saying one approach is better than the other. I think they sometimes are complementary. In other cases, the issue is what type of decisions are modeled. Planning a journey or making strategic decisions, for instance, residential location choice, are the types of decisions that I think is dominated by high-level cognitive processes. Driving a vehicle, the type dominated by low-level cognitive processes. Further thoughts on this would be welcome. For instance, how can modeling of low-level cognitive process increase the understanding of high-level cognitive processes and the reverse? It should also be noted that applications often not need process models, but solely models that predict choices such as random utility models. But process models will still be useful, as I see it, because when the goal is interventions to change choices, a process model would be useful. Process models may also be useful for understanding why choices are often suboptimal. That is, to identify the use of heuristics. So why contrary models? A pioneer of behavioral decision-making, Herbert Simon, who early questioned that expected utility theory can explain organizational decision-making. And for this, in 1978, he received the Nobel Prize in economics. He was a professor of psychology and a PhD in political science. I have read his autobiography with the wonderful title, Models of My Life. In his paper in Annual Review of Psychology in 1990, Invariants of Human Behavior, he argued that invariants discovered in the life sciences are frequently not general and not quantitative, but may nevertheless be very impactful. He and his colleague and collaborator, Alan Newell, referred to them as laws of qualitative structure. He argues, and I cite, psychology does not much resemble classical mechanics. Its laws are and will be limited in range and generality and will be mainly qualitative. Its success must be measured not by how closely it resembles physics, but by how well it describes and explains human behavior. Despite perhaps a more controversial statement today, I think that current psychology is still not ready for quantitative laws that predict behavior. Applications need to recognize this. Quantitative models may still be useful in testing qualitative theories. For instance, systems of propositions realized in computer programs, which was the kind of theories that Newell and Simon worked with. You could say they are useful because they are precisely wrong, but not vaguely right. So finally, what is the relation between a choice and satisfaction with the outcome? Kahneman et al. In the Quarterly Journal of Economics, 1997, made the distinctions between decision utility, anticipated utility, and experience utility. Kahneman has later connected experience utility to satisfaction and subjective well-being. Since results show that satisfaction with outcomes may not always correspond to the choice, satisfaction with travel should only, I think, cautiously be inferred from revealed choices. Several possible accounts of the discrepancy have been empirically demonstrated in psychological research. First of all, the obvious thing, a probabilistic outcome may by chance differ from what was desired or preferred. Second, people have a limited ability to anticipate consequences of their choices. People's preferences change over time and with context. And as a consequence of the variation with context, choices made compared to other alternatives. The outcome is experienced alone. Satisfaction is a well-researched topic in service research. Methods of measurement have been proposed, but may need further development and adaptation to travel services. Theoretical ideas have been developed and are tested in travel behavior research, investigating how different psychological constructs such as perception, control, beliefs, attitude, desire, intention, and satisfaction are interrelated. I think this is a line of research that currently has much promise of integrating psychology and travel behavior research to the benefit of travelers. quantitative models of choice processes should still play an important role. It remains to determine what this role is. I think the dissertation seemed to be, to me, to be a step on this way, on the way. So thank you and good luck in the future, Thomas. Okay,
Thanks
that's
a lot.
all.
Thanks a lot, Tommy. So yes, it was really great to hear about many kind of future research directions in this area. And as you mentioned, that it's a very worthwhile and interesting direction of the future of travel behavior research. So now moving to the question and answers. So there's one question for you, Thomas. I don't know whether you can see you. Let me just read it out. So the question is from Brett Smith. And the question is, I was just wondering on the DFT and the relationship with time, whether those answering quickly, we're processing less attributes and we're able to quickly compare alternatives by processing a smaller problem, and whether that helps to explain the predictability of choice.
Thank you for that question. It's really interesting. This has actually been what we've been looking at just the last few weeks. This is what I've been working on, is actually incorporating eye tracking information into decision field theory. So I hadn't done this as part of my PhD. It's something I'm looking at right now. That's a really interesting point. I haven't looked at the exact specifics of what an individual person is looking at. So maybe you're right. I think that people who are making choices quickly probably are looking at subsets of information. And I've also not looked at how gaze pattern changes over the course of completing the experiment. So for example, it might be that by the time you get to questions 5, 6, 7, 8, you're only looking at the key information that you've sort of worked out. So that's another thing to look at. So it's all preliminary in nature and nice ideas and nice things to look into. So yeah, thank you for that.
Yes, so any other questions or panelists? Okay, I don't see any more. So let me just remind you again about the future events that we are going to have. So let's just try to share the screens, which has the details. Just a second. Maybe I don't have the screen sharing feature. Anyway, it doesn't matter. So I have posted that information at as well. 2 upcoming seminars planned. The first one is going to be at the end of August, tentatively 31st August. That's going to be a presentation by Dr. Timothy Brathwaite, who won the 2018 Eric Pass Award. It will be based on his thesis, The Holy Trinity, Blending Statistics, Machine Learning, and Discrete Choice. And it will be followed by a discussion by Professor Eric Miller, who won the Lifetime Achievement Award in 2018. And then in November, possibly on 29th November, we will have a presentation by Dr. Shenhao Wang, who got the honorable mention in the 2019 Eric Pass Award for his thesis on deep neural networks for choice modeling. And it will be followed by a discussion by Professor Juan de Dios Ortuzar, who won the Lifetime Achievement Award in 2012. And we are yet to release the exact times because we want to see how the timing for this seminar works in terms of attendance, because we have audience from so many different time zones. So I think the time zone may be a bit different next time so that it's more favorable for the US West Coast participants. Let's see. Okay, thanks everyone again for attendance. Kostas, do you want to say anything more?
Oh, yes.
I want to thank you and Giovanni and Natalie and Christina for the amazing organization. This has been a tremendously well-organized event. Thomas and Tommy, thank you very much. I learned new things. Even old folks learn new tricks, or old dogs. Certainly, I want to thank all the participants for Pat's ceremony. Has been emotional, happy, enhanced our subjective well-being in a tremendous way. And let's go to the next. Thank you again. Pat, thank you for being there.
Thank you all so much. Really appreciate it.
Okay, so bye everyone. So hope to see you again at end of August.
Everyone.